Hello everyone, I'm Jae Chu, one of the instructors of this machine learning course. So this is already 12th week, and from this week we start to study deep learning. And as a first starting point, we will study multi-layer neural networks. So the objectives of this week's class is to understand some introductory materials of deep learning, and also how the neural networks, and especially forward propagation and its cost function. And let me start with some introduction to deep learning. So deep learning refers to artificial neural networks that are composed of many layers, and this architecture was inspired by how our brain works. And in general, we have the area called the artificial intelligence, and then within that, we have a smaller area called the machine learning, and then also within that, we call a deep learning areas. And this part of a machine learning and deep learning is based on some training of our model driven by our training data. So why is deep learning a growing field? It actually requires little to no handcrafted feature extraction. So previously, it was quite a big issue to extract out some meaningful and high quality features so that our machine learning algorithm can work well. But in the case of deep learning, without this kind of feature engineering step, just using the raw data, deep learning can handle effectively those data and then extract out some meaningful features, and then leading to some high classification performances. And through this process, it maintains the state-of-the-art performances in many important applications. And so, in the case of an image data, given this input image, as we go through this neural network layers, we first extract out some low-level features that might be useful for our classification and other machine learning tasks. And then in the later layers, the extracted features or informations becomes more meaningful than the previous layers, and so on. So in this manner, deep learning can gradually extract out some meaningful features from our input data, and that's the main component that allows this deep learning to work so well. And it has been applied in many different areas, including this game AI. So this is the snapshot of a DeepMind's AlphaGo. And then also it was so successful in the image recognition tasks such as face detection and recognition. And also other types of an object detection and recognition was so successful by using this deep learning architecture. Deep learning was also applied in even more complicated applications. So in this case, we give this single image, and then our deep learning model can actually generate some explanation about what this image is about. So this phrase like a plane flying in the sky with the landing gear down. So these sequences of text or explanations were automatically generated our deep learning model. And then also the another successful application of this deep learning is a machine translation. So given a sentence in one language, and then it can generate the corresponding sentence in another language. So this is called a machine translation, and machine translation performances became really higher after using this deep learning approach. And let me go into this neural network architectures a little bit more deeply. Again, this deep learning architecture is inspired by our brain structure, which has a lot of neurons that are connected to each other. So when looking at the one neuron, it has something called a nucleus, which takes inputs from other layers, and then this part will process these inputs, and then later on, this processed input is converted into some other useful information that can be transferred to other neurons. And thus, we actually mimic this architecture in our artificial neural network. And thus, when given this input, x0 and x1 and so on, they are weighted by some weighting factor. And then these weighted inputs are combined in the middle here. And then after adding some bias term or some constant term, it generates this intermediate output. And then this intermediate output is further transformed by our function f, which we call a activation function. And finally, this output will be transferred into another layer. By connecting this neuron with each other, we can construct this multi-layer neural network architecture. So given the original feature vector at the input layer, it will go through different layers and process these inputs further and further until we reach the desired output. Okay, and so in this case, so we have input layer and output layer, and also in the middle we have one hidden layer. So in this case, we call a two-layer neural network. But in the case of having two intermediate or two hidden layer, and we call it as three-layer neural network. And also alternatively, it is called a one hidden layer network or two hidden layer network. And let's understand how this neural net works. So the first thing that we have to understand is this forward propagation. So suppose we have this neural net architecture where we have three-dimensional input vector here, and then in the next stage we have two nodes in the next hidden layer that is processed by our inputs, and then also additionally we have some bias term, and then altogether these are combined into one single output layer. So let me introduce some notation here. So ai of j, in this case j is corresponding to the layer index and I is corresponding to the node index within a layer. So in this case it is placed in the second layer, starting from the input layer, and then the node index is 0, 1, 2, which uses a zero-based index. And then this capital theta of j is actually the matrix of ways controlling this function of mapping this input to output vector. So this transformation is basically defined by this linear combination of these given inputs. And then after obtaining this linear combination, we go through some nonlinear transformation, which we call an activation function. And in particular, we can use this activation function called sigmoid function, which is defined by this. And so in this function, it actually maps the input ranging from minus infinity to positive infinity into this fixed range of 0 to 1. So in this case, this idea was inspired by the fact that our neuron can fire or send the information of up to a particular amount. So after transforming this nonlinear function and then this mapping, output is the final output of this node. And this linear combination can be compactly represented by this inner product between these two vectors, where we have the row vector containing the parameter values and also this input vector. And then after doing this inner product, and then we obtain this linear combination. And thus this linear combination output is given as an input to this nonlinear activation function. And if we have this two node, the first node will have its own linear combination representation, and then the other one will also have its own representation. And by using the matrix notation, we can construct the matrix that contains all the coefficients, where the first row corresponds to the ways to generate the first node, and then the second row contains the ways corresponding to the second node. And then, given these are three-dimensional vector, and this matrix will transform this input vector into two-dimensional output vector, which corresponds to these two outputs. But these two outputs are going through some sigmoid function as our nonlinear unit. And then finally, we will have this two-dimensional vector of output node. And moving to the next layer, those two outputs will be working as our new input. And then we have some bias term, and usually we set it as 1, and then we also assign its own weight value. And thus, we also have the three parameters corresponding to these three edges. And that, those edges or ways are represented by this row vector. And then we have our new input vector. And then after multiplying them as an inner product, we will generate this linear combination, and then this linear combination output will go through our nonlinear function. And then finally, we will obtain this activation of this node at the last layer. And let me go through some real-world example of the dataset called amnesty dataset. So this dataset is composed of handwritten digits that corresponds to the label or digit of 0 to 9. And in total, it has 55,000 example for training and also 10,000 example for testing. So these digits have been size normalized so that their image size are all 28 by 28, and then also these input images are represented as a 2D matrix containing those pixel values corresponding to these image sizes. And then let's think about this example of an image, and then it can be viewed as this 28 by 28 matrix, where those values are corresponding to some dark region. So as we have a darker pixel, and then this value will become larger and larger, and the maximum value of this pixel is just 1. So it is normalized so that the range lies between 0 and 1. Using this amnesty dataset, we can construct a artificial neural network so that we can predict the given image's label information that indicates a particular digits ranging from 0 to 9. And thus, in the input layer, we will take this two-dimensional matrix representation of this image, but we can make them as a single vector by just cutting these matrices vertically and then concatenate them. And then in total, we will have 784 neurons or dimensions, which is the product between 28 and 28. And then let's set up the hidden layer that has 15 neurons or nodes. And then in the output layer, we will have a 10 nodes ranging from digits 0 to 9. And let's look at this code. And thus, let's focus on this input layer. And then the input size is this 784 by 1 matrix, where we constructed this input as a column vector. And then we actually add some bias term of 1 so that the linear combination can be done by using this input layer and then some constant term. And so it is the first layer output. Okay, and then the size will be 785 by 1. Then let's look at this edge part. So this contains the information of the linear combination of ways that will generate the hidden layer output. And then this weight has the size of 15 by 785. So you can think of this matrix of size of 15 by 785, and then we multiply our vector of 785 input vector, and then the resulting vector will be 15-dimensional output. And thus such kind of operation is done by this dot product. So the output size will have 15 by 1, and then this output is going through this sigmoid function or our nonlinear function transformation. And then the size will still be the same, and then we add one more node that contains this constant of 1, so that we can linearly combine the previous output and this constant to generate the next layer's output. Then the size of this hidden layer node will be 16, and thus A2 has the size of 16 by 1. And then let's look at this transformation that corresponds to all these edge weights. And then this edge weight will have the size of 10 by 16. So after doing this dot product between this edge matrix and then also the second layer or hidden layer output, and then the resulting size will be 10 by 1, which corresponds to this output layer. And then we can also go through this 10-dimensional output by using this sigmoid function, and then we finally get 10 by 1 output that corresponds to each of these nodes. And then let's suppose the resulting output is shown as this 10-dimensional vector. And notice that each value is all ranging from 0 to 1 because we went through the sigmoid function. So the sigmoid function output is always between 0 and 1. Then each of these sigmoid output can be thought of as the probability of being a particular digit label. So if we look at its correct digit label of 1, we can consider the model output of 0.8 as having 80% probability of being the class 1. And so this is a relatively high probability, so this can be considered as a good output. But let's look at another example where really large probability of 80% is assigned to the digit label 5, which is clearly the wrong case. So this case is not that good. And thus we can utilize this notion of comparing our desired output and the current output. So this is our prediction output, and then ideal output that we desire can be constructed as this vector, where we have 0 probability values for all the wrong digit label, and then 100% probability for the correct digit label. So we can compare these two, prediction output and then desired target vector, and then using the difference between these two vectors and then taking the squared value of them to consider their difference values, and such difference values corresponding to each digit label can be computed as these values. And then altogether, if we sum them up, and then we can consider how bad this output is as this value of 1.67. So our neural net can be trained or optimized by minimizing this resulting error, which considers the difference between this desired output and the model output. In this manner, we can consider our objective function that we want to optimize so that the model output can become as close as possible to the desired output. So in the context of the regression problem, we can consider the model output and the desired output, and then consider its squared differences and then their summation. And this is what we want to minimize. And in the case of a classification, we can consider other types of objective function. So in the case of binary classification, where we have only two types of labels, we often use this sigmoid cross entropy loss. But in the case of multi-class classification problem, we consider this softmax cross entropy loss. So these objective functions are optimized by gradually changing the model parameters so that the desired output is close to our model output. In summary, this lecture discussed some introductory material about deep learning, and we considered how the neural net works, and especially we studied the forward propagation and also the cost function. Thank you very much.